All right, so we have four small topics to cover today. We're going to cover voltage combination, current source combinations, voltage division, and current division. Each one of these topics are literally going to take 10 minutes or less. Okay, so let's start with voltage source combinations. And there are two different options for us here. We can have series connected voltage sources, so we'll look at that first. So let's say that we have a simple system containing multiple voltage sources in series. Let's call this VS1 connected to some voltage source VS2 connected to some resistance R. I'm going to assume a voltage drop of VR over my resistor having this particular polarity. And then I'm going to have some voltage source here, VS3, like so. And I am going to assume a direction for the current. And I'm going to assume my current is flowing clockwise around this loop. It's completely and utterly arbitrary choice. It's just going to explain where signs come from in a moment, right? So if I perform Kirchhoff's voltage law around this loop, I will get negative VS1 plus VS2 plus VR plus VS3 is equal to 0. I'm going to put VR on one side of the equation and all of the other terms on the other side of the equal sign. So that's going to look like VS1 minus VS2 minus VS3 or some equivalent voltage VEQ. Okay, so from the perspective of the resistor, it sees a single equivalent voltage that is a combination of the voltage sources. Okay, so notice what we have going on here with respect to the currents. Okay, so VS1 is where we started our loop or whatever. It winds up having a positive sign, and the current is leaving the positive polarity terminal. For the currents that are entering the positive polarity terminals, those wind up getting a minus sign because they are of the opposite polarity as that voltage source VS1. So effectively, the rules for combining voltage sources is simply, if the voltage sources have the same polarity, they add together. If they have the opposite polarity, you take the difference. How many of you guys have ever changed the batteries in a remote control? You have combined voltage sources in series. That is literally what you're doing when you put batteries in a remote. What happens if you put one of the batteries in backwards? It doesn't work, because instead of applying the full 6 volts, 9 volts, or whatever that you're supposed to do, you're supplying less voltage because two of those batteries wind up canceling each other out because their polarities are opposite. Okay, so voltage sources in series, pretty straightforward. You've literally been doing it your entire life. For those of you that have had, Game Boys and crap like that. Okay, anything that you've had to change the battery in, you have combined voltage sources in series. Now let's look at voltage sources in parallel. Okay, so this is going to be a little bit wonky here. Or it may seem a little bit wonky. So let's say that I have some voltage source VS1 connected in parallel to some resistor R connected in parallel to some voltage source VS2. Let's call this voltage drop VR. And then we're going to have two possible cases here. All right. Case number one, VS1 is equal to VS2. So if VS1 and VS2 are the same thing, what is VR? The same thing, absolutely right. VR would be equal to VS1, which we know is equal to VS2, right? Case number two is when VS1 is not equal to VS2. And here we run into a little bit of a problem, right? So if we performed Kirchhoff's voltage law, if we wrote a Kirchhoff's voltage law equation around the left-hand mesh here, we would see that VR is equal to VS1. If we wrote a Kirchhoff's voltage law equation around the right-hand loop, though, we would see that VR is equal to VS2. So how can VR be equal to VS1 and VS2 if those are two different numbers? Well, the short answer is it can't, okay? So when we are dealing with circuit analysis, if we ever have two voltage sources in parallel and they do not have the same value, we cannot apply circuit analysis techniques to solve the circuit because we're violating one of the fundamental rules of circuit analysis here. That being said, I could physically construct a circuit like this very easily, right? We have variable voltage sources literally all around this room. I could hook two of them up in parallel and throw a resistor between them, and I would observe a single voltage across my resistor. The reason why I can do this in a physical sense or make a physical circuit of it, but I can't do it theoretically here, is because physical wires have resistance that will accommodate the voltage difference between the two sources, right? So effectively, what you would see is that some amount of current would flow from the larger voltage source to the smaller voltage source. That's how we charge batteries and things like that. And there's going to be a small voltage drop across the wire, and that voltage drop will be whatever the difference of the two voltage sources is, okay? So just to reiterate, this case, perfectly okay. This case, bad, okay? Now, it may not seem obvious, but we actually deal with voltage sources in parallel very often, at least in the power industry, okay? So how many of you guys, or I guess, how many of your parents have solar panels and things like that on their home? Anybody? So solar panels are regularly connected in both a series and a parallel configuration in order to up the overall power rating of the system, right? So if you have a solar panel that's rated for, let's say, 24 volts DC, 6 amps, if you put it in series with another 24 volt, 6 amps solar cell, you have now a unit that is rated for 48 volts, because the voltages will add together because they're in series, but they can only carry a total current of 6 amps. If you put one of those 48 6 amp module or 48 volt 6 amps modules in parallel with another 48 volt 6 amp module, now you have 48 volts, but you have 12 amps of current carrying capacity. So you're increasing the power by putting those voltage sources effectively in parallel. I work for a company called Sabre Industries out of Bossier City. And I help to design battery energy storage enclosures for large scale power projects. Like our biggest project was a few hundred buildings. So this is about a 30 to, I think, $35 million contract where we supplied the battery energy storage component of that huge solar farm out in the Mojave Desert that serves the Los Angeles Water and Power District, okay? All that I do there is connect batteries or voltage sources in parallel, because that's what a battery energy and storage enclosure is a whole bunch of batteries connected in parallel. And then they have a charge balancing circuit to make sure that effectively all of the battery cells have pretty much the same charge so that you're not causing particular cells to heat up and explode because they're full of dangerous chemicals, okay? So batteries or voltage sources in parallel is something that is done an awful lot in the electrical utility industry, especially alternative energy. Okay. So now let's look at how we combine current sources. We're going to start by looking at current sources in parallel. So let's say that I have some current source IS1 directed up in parallel with some resistance in parallel with some current source IS2 directed up in parallel with some current source IS3 directed down. And for the sake of argument, let's say that my resistor current IR has a direction down. Okay. If I apply Kirchhoff's current law at the top node, where currents that are leaving are positive, what I will get is negative IS1 plus IR minus IS2 plus IS3 is equal to 0. I'm going to put my resistor current on one side of the equal sign. So I'm going to have IR will be equal to IS1 plus IS2 minus IS3, or some equivalent current. So much like we saw with voltage sources in series, whenever we have current sources in parallel, if they have the same direction, they add together. If they are of the opposite direction, we take the difference. So there's combining current sources in parallel. If we have a series combination, we would have something like this. So here's IS1, some resistance here. Here's IS2. Here is our resistor current, and I'm going to draw it on both sides here. And we're going to have two potential cases here, much like we had with voltage sources in parallel. So case one, IS1 is equal to IS2. How much current is flowing through our resistor? IS1, which is equal to IS2, right? We can determine that by applying Kirchhoff's current law at either the top left-hand node or the top right-hand node. What if IS1 were not equal to IS2? If we apply KCL at the top left-hand node, we would see that IR is equal to IS1. If we applied KCL at the top right-hand node, we would see that IR is equal to IS2. If IS1 and IS2 aren't equal, then our resistor current has two different values at the same time, which cannot happen, right? So this is also another case where we just have to stop what we're doing because our circuit analysis rules are broken. I cannot think of any practical case where it is even conceivably possible to connect two voltage source, or excuse me, two current sources in series that aren't carrying the same current. Okay? Connecting current sources in series, the only example that I can think of would be a cascode transistor amplifier. And even then, by definition, the two current sources in that they're connected in series, and they literally have to be carrying the same amount of current. Like they physically can't not do that. So there is no in my experience as an electrical engineer, there is actually no case where you will ever see this configuration. So just as a heads up. All right, so we have talked briefly about combining voltage sources and how to combine current sources. Does anybody have any questions regarding those topics before we move along to analysis tricks here? All right, I believe this is fairly straightforward. If you have any questions, by all means ask, but since nobody's saying anything, let's move along and look at voltage division. All right, so voltage division is really a trick, okay? It's a circuit analysis tool that we can use to calculate the voltage drop over any resistor in a series combination of resistances without bothering to determine what the current is, okay? So let's consider a series combination of resistors. And this derivation is going to look extraordinarily similar to what we did in our last class meeting where we talked about combining resistors in series. This combination of resistors, all connected in series, is part of some larger circuit. And let's say that we have some known voltage drop across all of our resistors. There must be some amount of current, I, flowing through all of the resistors. Okay. Since there's current flowing through the resistors, there will be a voltage drop over each individual resistor. Like so. And applying Kirchhoff's voltage law around this loop, we can find that our known voltage, V known, will simply be the sum of the individual resistor voltage drops, right? Again, to this point, exactly identical to what we did in class on Wednesday. I'm going to express all of these voltage drops in terms of that common current I. So that we're going to have I times R1 plus R2 all the way out to R sub n, like so. And from this, we can see that I is simply our known voltage divided by the total resistance in series. From here, we can use Ohm's law to say that the voltage drop over resistor R1 is simply I times R1, or whatever our known voltage was times a ratio of resistances, right? Where we're going to have R1 in the numerator, and then R1 plus R2 all the way out to R sub n in the denominator. We could do something similar for R2, Rn, or any resistor here, right? So voltage division in general says that the voltage drop over the ith resistor is going to be the known voltage times the ith resistor over the sum from I is equal to 1 to N. Actually, let me change these notations because there's too many I's and it's going to bother me. Let's say the kth resistor, like so. So effectively, what this mathematical jargon here thing means is if we're trying to find the voltage drop over resistor 3 out of a 5 resistor series combination, it's going to be R3 over R1 plus R2 plus R3 plus R4 plus R5 times the voltage. I've stumbled a little bit here, so let's work some examples and I think it'll clarify some things. And it's going to let us look at a couple of things as well. So let's say that I have a 10-volt source. I have a 5 ohm resistor. A 4 ohm resistor. And an 8 ohm resistor. And I want us to figure out two things. The first thing will be the voltage drop over the 5 ohm resistor with this particular polarity. And the second thing will be the voltage drop over the 4 ohm resistor with this particular polarity using voltage division. So using our voltage division relationship, we can see that V5 is just going to be our known voltage. So that's 10 volts because there's a total 10 volt drop over all of those resistors in series. And our numerator goes 5 ohms because that's the resistor we're trying to find the voltage drop over. And then in the denominator is just all of those resistors in series. So 5 plus 4 plus 8. So that looks like 10 times 5 is 50 over 17. We didn't have to bother solving for a current whatsoever, right? So this is just a little bit quicker of a way to solve for the voltage drop across a resistor in a series combination. Okay. Now, you guys tell me what I'm going to do to solve for V4. You're absolutely correct. Next. So it's the exact same thing, except now we're going to have a 4 ohm resistor in the numerator because we're finding the voltage drop over the 4 ohm resistor. But we also need to include a negative sign out front. Can anybody tell me why we need to include a negative sign out front? Because the polarity is opposite what we would expect. So think about it from this perspective. In this case, we know that our known voltage is the thing that's supplying power to this resistor network, right? So when we calculated V5, the current was flowing into the positive polarity terminal. So we had a positive sign. When we're calculating V4, the current's flowing into the negative polarity terminal. So we need a negative sign. Okay. That's how voltage division works because that's how Ohm's law works. All right. So you might be thinking to yourself, this seems pretty limited in its application because it requires us to have series resistors. That's not entirely true. It just requires us to be able to combine things together to make it look like they are in series. Okay. So let's say that we had a situation like this. We have a 6-volt source. Let's say that we have a 10 ohm resistor here. a 9 ohm resistor here, and a 18 ohm resistor here. And we want to figure out what this voltage Vx is. So we no longer have a simple series combination of resistances connected to our voltage source, but we can still apply voltage division by treating the 9 ohm resistor in parallel with the 18 ohm resistor as a single equivalent resistance. And because they are in parallel, they have the same voltage drop over them. So we could say Vx in this case is just going to be 6 volts times 9 in parallel with 18. So that's 9 times 18 over 9 plus 18 divided by 10 ohms plus 9 in parallel with 18. If I'm not mistaken, 9 in parallel with 18 is 6. So that's going to look like 36 over 16, which would be, doing better math, let's see, 18 over 8, 9 over 4. So we can make voltage division work for us if we're able to combine resistances, okay, and make it look like it's simply a combination of resistances in series with our voltage source. Okay. So, any questions about voltage division? Fairly straightforwardish, right? Everybody okay? Now let's take a crack at current division. This is another tool. Just meant to save you a little bit of time by eliminating some steps in calculating the amount of current flowing through any particular resistor in a parallel combination of resistances. So let's say that we have some resistance here, R1. Some resistance here, R2. All the way out to some resistance here, R sub n. This parallel combination of resistances is part of some larger circuit. And let's say that we have some known amount of current flowing into this network. Okay. So since there is current flowing through these 3 resistors, we should expect that there is some voltage drop across these resistors. And because all of the resistors are in parallel, that voltage V is common to all of them. I'm going to say that my current will split in these directions, right? So all of our resistor currents will be in the down direction. And now I'm going to write a Kirchhoff's current law equation. So I can say that I known is equal to IR1 plus IR2 all the way out to IRN. And I can express all of those resistor currents in terms of that voltage V, such that I will have V times 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. And from this, I can say that V is I known divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. Okay. I'm going to put this in blue because this isn't really part of the derivation. It's just something that we can observe. This is literally just I known times the equivalent parallel resistance. So using Ohm's law, we know that I1 is V divided by R1. And I'm going to express this slightly differently. V times 1 over R1. Or substituting in our relationship for V, we're going to have I known times a ratio, much like we had for voltage division, where we're going to have 1 over R1 in our numerator, and then 1 over R1 plus 1 over R2, all the way out to 1 over R sub n in our denominator. So we have a very similar form as we had for voltage division, except that instead of the resistor values, we're adding the sum of the resistor, excuse me, the reciprocal of the resistor values. Okay. So let's put this into practice as well. Let's say, let's do something simple. That I have 4 amps. I have a 2 ohm resistor here. And a 5 ohm resistor here. And I want to figure out this current I2 and this current I5. Applying my current division equation, I'm going to have my known current of 4 amps. Since I'm finding the current through the 2 ohm resistor, I'm going to have 1 over 2 ohms. Divided by 1 over 2 ohms plus 1 over 5 ohms. I'm going to do a little bit of mental math here. So 1 over 2 is the same as 5 over 10. So I'm going to have 5 over 10 over 5 over 10 plus 2 over 10. So that's going to look like 5/7. So 4 times 5/7 is 20/7 of an amp. You get that in the calculator? Yep, great. When we're finding I5, we're going to do the exact same thing, but because the current is in the opposite direction as what we would expect, we're going to wind up including a negative sign. So negative 4 amps times 1 over 4 ohms, excuse me, 5 ohms. There is no 4 ohm resistor. One over 2 ohms plus 1 over 5 ohms. So that's going to be 2/7 times 4. So negative 8 over 7 amps, if my mental math is correct. All right. Yeah. So this is a simple and straightforward application of current division. Now let's mess with things a little bit and see how we can expand the efficacy of current division. So let's say that I have a circuit like this. Yeah, that'll be fine. And I want to figure out this current IM. So just want you guys to look at something here really quickly, right? When we derived these relationships for current division right here, we have a current flowing into a parallel resistor network. In this circuit, we have literally no elements in parallel, but we're still going to be able to apply current division. Okay. So the reason that we can apply current division is because that 4 in series with 6 is in parallel with the 3, right? So we can do effectively resistor combination, much like we did using voltage division a little while ago, to make this look like there's a known amount of current flowing into a parallel resistor combination, right? So let's start with the ratio of resistances here, right? So the branch that I'm trying to find the current through has a total resistance of 4 ohms plus 6 ohms. And then the two branches that are in parallel are the 3 ohm branch and the 1 over 4 ohm plus 6 ohm branch. Now, what's my known current here? 5 amps, absolutely right. And so we can throw this into our calculator really quickly, and I'm not going to do the mental math for this one because it's going to take too long. 5 times 1/10 over 1/3 plus 1/10. 15 over 13 amps. What's your question? The 10 ohm resistor. I was waiting for this question. Why isn't the 10 ohm resistor showing up in this equation? Absolutely fantastic question. Exactly what I was expecting. How much current flows through the 10 ohm resistor? 5 amps. So we know that the current that's entering that parallel combination is 5 amps. So effectively what we're saying here is that since the current doesn't have an opportunity to split, the 10 ohm resistor shouldn't show up, right? Because current division requires the current to split among parallel resistive paths. Exactly right. Great question. So this is how we can apply principle of current division to something that really doesn't look like we should be able to do it, but by using resistor combination techniques and simple observation, we can figure out how to force this square peg into a round hole. Yes. All right, so that is all that I wanted to talk about for today. Just 4 small topics: combining voltage sources, combining current sources, applying the principles of voltage division, applying the principles of current division. You have an in-class assignment as well as a mini lab for today. So choose your own adventure. If you have any questions about anything, I would be more than happy to help.